Okay, so last time we talked about basically optimizing our database accesses, right? So we know about queries, we know of those things. And last time we talked about physical level or physical storage level optimization, such as creating or building indexes. What are the different types of indexes that we can create that would, depending upon the queries, that would make our queries faster. And the reason was that how do we organize the data in our table, because usually in the physical level actually, because usually the data is stored in more or less on all of most of the databases, the data is stored as a heap file, right? Anything goes, Mad Max situation, anything goes anywhere, there is no ordering whatsoever. And that is sort of the best way of storing data at this point, because sorting has a lot of overhead, right? We don't really want to sort something when we don't actually know what the possible queries are, right? I can sort by a particular attribute, but that might end up not being used at all in another, in some queries, in most frequent queries, right? So it's best to have your data in heap structures, but then build indexes on top of that, that the database is not smart enough to create on its own, but that actually speeds up lookups and all of those things. Today we are going to, so given that today we are going to drive the discussion a bit upwards in a more abstract sense, in the logical level. So given a particular query, how does your database make that query faster? Right. So in essence, we will talk about these things. So we need to understand the different aspects of executing a particular query in a particular way. Right. So it is not always straightforward as to how we write our query should not always be the same way that our queries are executed. Because and so this has nothing to do with indexes at all, right? So I might write a query that is completely in a correlated way, but your database can be smart enough to figure out that, you know what, this correlation is not required, I can actually decorrelate it into two separate computations and then execute each of them separately so that I can make it more faster, right? So things like that. So we basically will be talking about the query planner and how your database essentially plans over your queries. Okay. So yes, so we will look at higher level query evaluation details. And this is where your relational algebra operations come back again. Uh, in almost all databases, your queries are again in English, right? SQL has means that it is a structured English query language, right? So it has to be converted into some form of formal mathematical definition for us to be able to formalize and then plan over the things that we can do and then figure out an efficient way of doing that, right? So how are our relational algebra operations implemented in the database? Your database will look into, so when it is executing something, it will look into this relational algebra operations that is allowed to it. And based on that, it would try to use these details to sort of plan and optimize your queries, right? So we will look into different ways that your database actually does that. We will also look at some exceptions. For example, the MySQL's join operation. I always say that MySQL can't do a full outer join, right? So we will also need to understand why it can't do it. So in essence, in order for MySQL to actually have a full outer join, the set of operations that okay, so I am trying to perform a particular thing and your database sees that, okay, I need to perform this particular relational algebra query. I have these tools in my toolbox that I can use to actually implement that query and execute that result. Those tools can differ across database implementations, right? Not all databases may have all sorts of tools. Some database may have like a bubble sort algorithm to actually sort out your data. Some other a more advanced database will have a merge sort and a quick sort implementation or a team sort implementation for that. Other types of things, hashing abilities and other sort of details we will talk about. But um, essentially your database then plans over these tools to figure out the best possible way to execute it. And we will also see that um, in order for MySQL to actually perform the full outer join, the way it is built and the tool sets that it has does not allow it to do it efficiently, right? So the and that is why MySQL does not have a full outer join, because it is very complicated and it has to make, if it wants to have that ability, it has to make a lot of structural changes to its machinery to actually make a full outer join work. And that is why usually we don't have that in MySQL. Okay, so whenever we write a query, your database actually goes through three basic steps, right? Firstly, it parses the query into uh, yes, it parses the query into an internal representation of that particular plan, right? So the term for that, I believe I wrote it here, is abstract syntax tree, right? So essentially it takes the query, builds a pipeline or builds a tree of those relational algebraic nodes, and then has that representation, and then it transforms that representation into an optimized execution plan, so that I can then transform this mathematical operation into a more optimized plan. And then I evaluate the optimized execution plan. Then the executor says, you know what, these are the possible plans that I have that can be executed. Out of this was the best one, that is the most fastest, and you need to execute this one. And then the executor executes that particular plan, right? So we would look into the traditional relational algebra components that we talked about, those six, union, set difference, select, project, all of those things. But we will also look into some other things that are not inherently given by the relational algebra model, like sorting and limit and offset. Those sort of things are also defined when it's those sort of things are also something that it looks into when it is actually planning what to do. So I know that this sort of feels very vague right now. So let's take a example, right? So let's say that we have this very simple query. Select T1.a from T1 comma T2, where T1.b equals to T2.b and T2.c equals to 10. So we have two tables. We are joining with respect to the b attribute, that is T1.b has to be equal to T2.b and T2.c has to be 10, right? And so, and basically then projecting out T1.a value. Right, so basic stuff, very basic stuff. So this particular query can then be translated directly into a relational algebra model, right? So we know that it is T1 comma T2, so we need to perform a Cartesian product on that. So T1 cross T2, and then essentially we perform a select operation, T1.b equals to T2.b and T2.c equals to 10, right? And then we project out T1.a, right? These are all fairly simplistic stuff, right? We talked about these things in the first week, right? So once we have this relational model, your database actually creates this pipeline of the things that it has to do. So you can see that this is sort of like the pipeline that it looks like. We have table T1 and table T2, and these are your plan nodes that we need to execute. And whenever we have a Cartesian product, your database actually replaces that with theta joins, right? Remember what theta joins were? Theta joins were conditional join operations that we can join on any condition that we want, right? So setting that to true essentially means we are performing a Cartesian product. So it says that, you know what, join these two tables and then select out with this predicate, that is T1.b equals T2.b and T2.c equals to 10. And now that we have this result from this select operation, we project out the details that we want from that set of rules, right? So does everyone sort of understand how we got to this particular pipeline or this particular diagram from this particular relational algebra query, right? Or this SQL query for that matter. Does this make sense? Right? Simple enough stuff, right? Okay. So Anybody else? Any questions on this? Joel, Devon, Divyasri, Aha, Leon? No? Cool. Okay. So, so now comes the question that we have this particular mathematical formulation, and imagine yourselves as part of the as being a database, right? We have this particular operation. How do I optimize this? So first, what your database would do is generate alternate formulations for your query that would result in the same answer. So the original formulation was perform a Cartesian product, perform the select operation, and then project it out. But it sees that, you know what, instead of performing a complete Cartesian product, because that is quite expensive an operation, right? That is combination of all possible things. We would like to reduce the number of rows in a table and then perform a join operation, which would make it much more faster because less number of rows to be computed, right? So it can actually push the select query for this particular thing, that is t2.c equals to 10. Maybe only select those rows in the first place, since it's an AND operation, only select those rows in the first place, and now directly perform a theta join or a natural join for that matter with that table. So we have basically converted a Cartesian product into a natural join with a table T1 and a smaller derived table T2 from T2, right? So that would be another formulation, and as you can see that both of these would still return to me the same result. But one of them, although in terms of relational algebra, both of these things are the same thing, right? But one of them, in terms of your database, one of them would be comparatively faster than the other, right? Or we can say that, you know what, I'm going to perform this join operation first and then filter out the rows that have t2.c equals to 10. So first perform a theta join, always try to avoid Cartesian products as much as possible, filter out it into a theta join, into a natural join for T1 and T2, that gets us a certain number of rows, and then perform the select query, right? And then the project operation is there. So out of these possible formulations, now the database asks which one is the fastest. So the question we are always asking is which one is fastest, and that usually involves some sort of a cost, right? Or some sort of a heuristic cost. So your database then follows certain set of rules to statistically predict what would be the cost of these queries without actually executing them. I want to know what are the individual cost of these plans without actually executing all of them, right? Because that is why, right? So one way would be to have some heuristic rules on top of it. So let's say that I want to select as early as possible whenever I'm executing a query. That would mean that I'm reducing the number of rows as early as possible before actually performing my join operations or any sort operations or whatever operations, right? And that reduces my overhead. So those sort of heuristic rules are there that can, some databases apply that. So perform select as late as possible, perform sort as, perform select as early as possible, perform sorting as late as possible. Another type of cost would be what are the actual estimated costs of executing this query. So that would include the disk access cost, the CPU cost of executing that thing, loading that into memory. What your database would have some vague estimates about what those operations might cost, and then convert this relational algebra formulation into getting a particular CPU cost or disk